Okay, what I want to do is I wanted to make a video because I know several of you requested it because you were out on Monday due to ACT prep stuff. So what we did on Monday is we basically introduced the concept of projectiles, and I want to make sure everybody kind of has an idea what a projectile is and what are some of the kind of characteristics of it. And then what I want to do is kind of work through an example problem so you can actually kind of see how you can apply some of the stuff that we're talking about. So first off, I want to kind of introduce what a projectile is. Projectile, when we use that word in physics, basically what it means is any objects that's going to be traveling through space. And in this particular case, the space that we're talking about is not like outer space, but literally like just a vacuum. Okay, so that's one of the big things, is that when we deal with projectiles, we're going to make a big assumption that these projectiles are in a vacuum. Okay, and that's going to come into play kind of later on, because we're going to use this to kind of make some assumptions about projectiles themselves. And that major assumption that we're going to make is that there's not going to be any air resistance. Okay. So we can safely assume if we have a projectile, there's no air resistance, and because there's no air resistance, there's only going to be the acceleration of gravity. Okay. So the only acceleration is gravity. And also, just kind of as another trait of projectiles, is that what we can say is that all their paths are parabolic. Okay. And we're going to use that also kind of to help us kind of solve some of the different kinematic quantities that we can have for each of these projectiles. Okay, so what I want to do is kind of start with an example and kind of show you how you can apply each of these things right here to solving a projectile. We're going to start with a real basic type of projectile, and that is going to be a horizontally launched projectile. Okay. So let's take this projectile. I'm going to put it onto an elevated surface that is 10 meters. And I'm going to give it an initial velocity of 100 meters per second. Okay. Now, the reason I'm calling this a horizontal projectile is we're going to launch this thing at a degree that is equal to 0. Okay, so 0 degrees. Okay. Now, this is the information we've been given. What we're going to try to solve in this particular example is what we're going to call the range, how far it is from the base there. Okay. So this is kind of the general setup. It's launched at 100 meters per second. It's off of a 10-meter high launch platform. It's at 0 degrees, and we're trying to find the distance or the range, whatever you want to call it. Okay. So let's go through a list of the stuff that we know from the problem, and then some other assumptions that we can make with horizontal projectiles. Okay. First and foremost, the initial velocity in what is the x dimension is going to be 100 meters per second. The reason being is that since this is a horizontal projectile, the muzzle velocity is the velocity in the x direction. Okay, now that is going to be different when we have an angled projectile, but because we are horizontal, that is kind of one of our first major kind of assumptions, is that whatever the muzzle velocity is going to be that velocity right there. Right? Now, another thing that's kind of based on that is because we have no air resistance, the final velocity is also going to be equal to 100 meters per second in the x direction. There's no acceleration, so there's not going to be any change due to the fact there's no air resistance. Right? And this next one is probably the biggest of all the assumptions, and this is actually extremely important to solving these kinds of problems, and that is the fact that the initial velocity in the y direction will be 0 meters per second. Okay? Now, the reason is that since we are shot completely horizontal, there is no y component of the muzzle velocity, which means that value is going to be 0. Okay, and I'm going to put a star next to this one because it's that important. keep in mind this only applies to horizontal projectiles. Okay, so keep that in mind. Okay. Now, we've already mentioned it earlier, but there is no acceleration in the x direction. The y direction is going to be gravity, and I'm going to use 10 for that one. Okay. All right. The only other piece of known information that we have is that the height that we're going to launch it from is going to be 10 meters. Okay. Okay. Now, as far as unknown information, here's what we do not know. Okay. Ultimately, well, we don't know what we're trying to solve, which is a range. We don't know the final velocity in the y direction. And we don't know the time. Okay. Now, on projectile problems, if it's not given to you, one of the very first things you should try to solve is your time, because you can't really do a whole lot of other solution with the problem itself if you don't know what the actual time is. So what I would suggest is trying to make that your number one priority if it's not given to you. Okay. Now, because our paths are parabolic, that means our time is going to be, well, problematic sometimes. The reason being is that due to the parabolic nature, that kind of lends itself to a quadratic equation. Okay? And what I mean by the quadratic equation is if you have your formula sheet, the second equation on there, follows this format. X equals x naught, so position final equals position initial plus 1/2 the acceleration times the time squared plus velocity initial times time. Okay. If we set this equal to 0, we have what is in essence a quadratic equation. Okay, so I'm going to go ahead and set this equal to 0, and we're going to get x naught minus x plus 1/2 at squared plus velocity initial times time. Okay. Now, we are going to solve for time in the y dimension. So I'm going to go ahead and switch all these variables over to y variables so we can kind of make it match the dimension that we're going to be dealing with. Okay. So here's what we have. It is a quadratic equation, but if there's one saving grace with these horizontal projectiles is we don't have to actually use the quadratic equation, which is a big relief because a lot of people don't like quadratic equations, myself included. So what I like to say is you can kind of neuter this equation, and here's what I mean. We can neuter this because we can cut this little piece off right there. Okay, and once we cut that off, and the reason we can cut off, I should probably say that first, is that because our initial velocity is 0, we don't have to really concern ourselves with that particular term. And once we get rid of that term, once we have neutered it, we've really kind of tamed this equation. And reason is that we don't have a true quadratic anymore because we don't have that term in two different places. It's now just right there. And that's actually a really good thing because what that can do for us with these horizontal projectiles is it makes it a heck of a lot easier to solve for time. So what I'm going to do now is I'm going to show you the algebra to actually solve for time. Okay. The first thing I'm going to do is I am going to I'm going to move these over to the left side. So here we go. So I'm going to get y minus y naught. I just moved them both at the same time. No pun intended. 1/2 ay times time squared. Okay. Now, because this is y final minus y initial, I'm going to go ahead and change that to delta y. And I'm going to go ahead and multiply both sides by 2. So I'm going to get 2 delta y equals ay t squared. I'm going to go ahead and divide by ay, which is really just g. So I'm going to go ahead and do that as g right now. And last but not least, go ahead and do the square root. Okay. So here's what the final version is of this particular equation. Okay. Now, I'm going to put a circle around this equation, mainly because for whatever reason, this equation pops up a whole lot of time on old AP exams. Once again, no pun intended. For whatever reason, lots of multiple choice questions in the past, a few open response questions will actually utilize this equation. I don't know why that equation pops up more frequently, but it does. So what I like to tell students is have that kind of in your back pocket, so to speak. Have that, as something you should probably memorize, going to the test knowing this equation. Because technically, if you have to use this equation in an open response, you don't really need to do all the algebra. What you do need to do as a minimum is to basically write the original equation from the formula sheet and then write that equation. You don't have to show the algebraic steps unless it specifically asks you to do that. But if you can know that one equation, it'll make your life a lot easier when it comes to dealing with horizontal projectiles and trying to solve time. Okay? So what I'm going to go ahead and do now is go ahead and plug in my information to this and go ahead and get my time. So I guess I'll just do it right here. Okay. So my delta y was final position, which is 0, by the way. I forgot to mention that earlier, but I'm going to say that the bottom is 0 meters. So I'm going to end up at 0 meters and start at 10 meters. So my delta is going to be 0 minus 10. And then that's going to be divided by negative 10 for gravity. Okay. And then, of course, that's going to be underneath the square root. So basically what I'm going to end up getting is I'm going to be getting, if I look at this and kind of simplify it, I'm going to get root 2 as my answer. So my time is going to be we'll just say 1.4 seconds and round it to the tens place there. Okay, so that's the time. Now, we don't want to lose sight of what we're actually trying to do in this problem. What we're actually trying to do is we're trying to solve for the delta x. But the problem is we cannot solve the range if we don't know the time. So we had to do the time first to be able to get to the range. What I was saying earlier is you got to have the time to be able to do basically anything else in that particular equation. That's why it should always be one of the first things you solve. Okay, now what we're going to do at that time is we're going to use that time to calculate the range. And the way we're going to do that is we're going to use this equation, which is not on your formula sheet, but it is the average velocity equals displacement over time. Now, most of the time when we refer to this equation, we just say it's the plain old velocity equation, displacement divided by time. This is just the average, but that's not a bad thing in this case because we don't have an acceleration in the x direction. So the velocity we have is the velocity we'll always have. So no acceleration. So we can use 100 for our velocity. This delta x right there is going to be our range. So if I just do just a little bit of quick algebra right here, I'm going to get the average times the time equals my displacement. Okay. What we have then is we have our delta x, which is 100, and that time that we just solved. Now, I'm going to talk just a little bit more about that because sometimes people are confused about the time. But in two dimensions, here's how time works. While this object is falling downward vertically, it's also moving forward at the same time. Okay? Once again, no pun intended. Moving forward, falling down. And the reason it's the result of that, the fact that it's moving forward and falling down simultaneously, is the reason we get that kind of curved path. What it really means is that 1.4 seconds in this particular case means it's going to spend 1.4 seconds falling down to the ground and 1.4 seconds moving forward. Okay? What that means is that the time it's in the air is also the time it's moving forward. So we can safely use this number, 1.4 seconds, to figure out the range it's going to move forward in that period of time. And if we look at that, that's a pretty easy calculation. 100 times 1.4 gives me 140 meters as my range. Now, just to kind of reiterate everything that we've looked at, the main key, the main focus was to solve the time. Okay? Don't forget that on a horizontal projectile, we know this crucial piece of information about the velocity initial being 0. The reason information is so crucial is because it helps us to kind of temper the quadratic a little bit and kind of take out a little bit of the sting out of it. And instead of turning into a true quadratic, it just becomes kind of just a basic, simple algebraic problem there. Right? In closing, don't forget about these important things with projectiles, that projectiles, are in a vacuum. There's no air resistance, and because there's no air resistance, that velocity will stay constant. I hope this video was helpful to you. If you have any questions or anything, feel free to let me know. Send me a message on the Google Classroom page. If not, I'll see you guys next week. Have a good day.